Hello and welcome to this webcast. I am Alistair Freeland, and with me is Professor Jean-Louis Reymond from the Department of Chemistry, Biochemistry and Pharmaceutical Sciences at the University of Bern in Switzerland. Professor Reymond, thank you so much for being here.
Yes, thanks for inviting me. I look forward to the discussion.
So Professor Reymond, the emergence of multi-drug resistant pathogens has become a concern over the past decade, and this has prompted quite a search for alternative antibacterial agents. Now, antimicrobial peptides are a relatively new weapon against bacteria and often said to be the new way for bacterial infections, especially since more and more microbes are becoming resistant to traditional antibiotics. So in what way do antimicrobial peptides differ from the more traditional treatments?
Well, the first thing that is clear is that the problem of antimicrobial resistance is coming from the overuse of antibiotics. And so part of the answer is also the use. But indeed, once you're faced with a multi-drug resistant bacterium, you have to hit it stronger. And what these antimicrobial peptides do, most of them, is they're really a lot more toxic on bacteria. So the resistant development is almost impossible. And that's a different thing. And the reason we didn't have them before, because they are relatively new, but they're originally found in nature, is that the manufacturing cost is, of course, somewhat higher than traditional antibiotics. But that's in the world today, maybe that's not a problem, because you want antibiotics that you don't overuse. And you know, the curse of antibiotics is having been so cheap that they can be overused. So, you know, that's what happens with AMPs is a different approach, probably a bit of a more luxurious approach, but to really hit it very strong, this bacteria. And then you can go to these very, very superbugs that will not die otherwise.
And your recent paper, can you tell us a bit more about what your expectations were when you started work on this project, and also about the key results of the paper?
Yeah, so I mean, we have quite a program on antimicrobial peptide with the originality departing from traditional approaches that we use more like computational approaches to search chemical space and find original structures. Of course, going back to some patterns that are known. And it's relatively easy to find some activities, but then, you know, when you start to look at these multi-drug resistant and you want to mitigate toxicities, and it becomes harder. And we were looking at these, what we call bicyclic peptides. So there is a stabilization of the structure by a staple, which we discovered almost by searching randomly, in the sense that we didn't have a precise structure in hand. And then two things happened. We discovered that, in fact, there was an alpha helical conformation in the bicyclic peptide, which is what you usually have in antimicrobial peptides. And then by pure chance, the student working on it decided to change the chirality of almost half of the residues. And the reason he did that is because he didn't have an idea of the structure. So normally when you scramble chirality, you have a loss of conformation, and for AMPs, this would mean a loss of activity. And in this case, we had the surprise that the activity was preserved, the toxicity decreased, and the helical structure was also preserved. So it goes against everything we know about helical peptides. They're not supposed to fold when the chirality is scrambled. So it was really a cool discovery to find something surprising in these structures. So yeah, it's an unexpected discovery, which might have more consequences, because if you can start designing helical conformation with what is called mixed chirality, so both the natural conformation and the Ds, and you can also think about stabilization against proteases and also mitigating toxicities with an effect we didn't expect. So it's really interesting as a new dimension to to explore the possibilities to optimize the compounds.
From listening to you, you're also optimistic that antimicrobial peptides can play an even bigger role and more important role in future treatment, new treatment options.
Yeah, well, one thing is clear is that you can, once you start to look for peptides that hit bacteria or fungi in this class of antimicrobial peptides, which work by disrupting biological membranes in general, then you find that you do find these activities, and they are strongly depending on the sequence. So it's not so easy to find them, but you find them. Mm-hmm. But also at the same time, you find that it's difficult to be selective. So the main criticism against antimicrobial peptides is say, wow, wait a minute, it's active, but it's also toxic. And indeed, the difficulties that there has been in clinical use are linked to toxicity. Mm-hmm. And of course, that's the difficulties that you can face in any drug development. And what I think we find with the way we approach the problem, also from this chemical space point of view, where you look at an extremely broad diversity of sequences, is where you realize that the amount of possibilities that you can play with are enormous. And nobody has even scratched the surface. Most research has been done on naturally occurring sequences and not doing too many changes, but there is so much more one can do. When we are, in every project we make totally surprising discoveries that suddenly we have a compound where the toxicity goes down and the activity stays up. So my belief is that, yeah, okay, you can criticize that a lot of them are toxic, but you just need to search for the sweet spot where there will be a winning compound. And there are several compounds in the clinic, for example, for topical use, where toxicity is less problematic. The application also for inhalable peptides for cystic fibrosis, also where, let's say, the acute toxicity is less of a problem. So there are plenty of options that are being looked at. And I think it's only a question of searching carefully enough.
And so searching, as you say now, so what are the next steps that you are working towards in your research? Can you tell us a bit more about that?
Yeah, so of course, we are a group of chemists, and then, of course, you work through your simple biological assays in vitro, and then you have to move towards better toxicity assays, consider in vivo assays. And the more you make your biology complex, the less you can test the number of compounds. You have to mitigate. And so I have a European project on that where we have a bit more funding, so we can establish a more advanced screening platform and then start to move compounds into the more challenging assays. And it means, for example, that we had, that most of our compounds are not going to be good, and suddenly we find the ones that we can continue and tune their activities. And the strength of the approach, the way we do it, is we make the compound by chemical synthesis. So this goes extremely fast with peptides. You can produce tens and tens of peptides quickly and test. So by having all this running in the same lab, we are relatively fast in doing these optimization cycles. And I think this gives you a very fantastic option to progress quite far, I think. Well, one thing is what I find in our research that pays off a lot is to really analyze the compounds carefully, the way they act, to do detailed experiments, try to understand, because there is this approach which is probably coming from the fact that there is a lot of government program telling to people, yeah, just screen a lot of compounds to find the magic compound. But in reality, especially in these AMPs, you just don't screen blindly. You have to make stepwise progress, understand what's going on, modify structures, and progress in an informed and intelligent way. And so anyone working in this field must be very well aware of this, not treat the bacterium as a simple organism. And so the sophistication of the science that goes into getting the right antimicrobial is the key, I think. There's nothing simple. Mm-hmm. And we have the tools to do it.
Superb. Professor Reymond, thank you very much for your time. And I wish you all the very best for your further research and for this project that you're working on. and hope to see you again in the future. Thank you.
Thank you very much. Yeah.